Okay, so thanks a lot for the invitations. So sorry to have modified slightly my talk. I've decided to be slightly less ambitious and to present you in some generality the link between motivic homotopy theory of Morel and Wojewicki and the theory of motives, of rational motives, of Beilinson motives, in fact. Okay, so and first of all, I'll give you the plan of the talk. I want to recall to you the classical setting of homotopy theory in algebraic topology. And especially I'll present some theorem which will be a kind of model for the link between the theory of Morel-Wojewicki and the theory of Beilinson, let's say, or Wojewicki.
So actually most of our listeners have already heard about Morel-Wojewicki stable homotopy theory, so maybe you could skip some
details.
Okay.
So everyone knows Morel-Wojewicki's homotopy theory, that's what you said?
So maybe not very well, so if you want to put a stress on some particular result, yes, but they know the basic
of Morel-Wojewicki's theory.
The basic plan,
okay.
I would say.
So I'll be quick on this stable homotopy.
But usually it was in this building. Usually people discuss motives over a field. So this is
okay.
a difference. So you may say what is the main differences when you consider motives over a base.
Okay. And then I'll speak about the link with Grothendieck motives and Beilinson ones. Okay. So just let me recall briefly the theorem that I have in mind in homotopy theory. Maybe it's not so well known. So in homotopy theory, I usually consider topological spaces or equivalently simplicial sets up to weak homotopy. Equivalences. And usually I'm always considering pointed topological spaces or simplicial sets. Okay, so a weak homotopy of topological space, weak equivalence, is just a continuous map which induces an isomorphism on pi I for any I. Okay, and so this led us to a good category, which is the homotopy category. Let's say unstable homotopy category. Okay, and so the first use of this category is its link with cohomology theory. So I just recall that if we consider the singular cohomology theory, which to any topological space associates some cohomology space with coefficients in R an abelian group, then we have the first representability theorem of maybe of history, I don't know. And so there exists the so-called Eilenberg-MacLane spaces, which are denoted KAN, which I will consider as object of unstable homotopy category such that for any reasonable topological space, let's say CW complexes, the homotopy classes of map from X to KAN, so these are maps computed in this category, is in bijection with the nth singular cohomology. Okay? So to make this, so you see that in the homotopy category we can represent each functor if we fix some index n, but we would want a true representability theorem. So let's recall that underlying all this is the Braun representability theorem. I just present this in the case of singular theory, but theorem. And so we need a category which is more general than the category of the unstable homotopy category. And the reason for that is because of the stability property of singular cohomology, which is the following. If you take now I take a X to be a pointed space. Sorry, if I should pull the tilde, do you know this is reduced cohomology theory? Okay, and so it is well known that the reduced cohomology, singular cohomology theory satisfies this stability property. The cohomology of S1, the topological circle smash X, is isomorphic in degree n, is isomorphic to the same cohomology in degree n-1 of X here. Okay, so now if we translate that in terms of this representability theory, we obtain that the homotopy classes of map from S1 smash X to KAN are isomorphic. Maybe I put, yeah, okay, no. To X, K, A, N-1, like this, okay? Now I pass to the detail, but this is the suspension functor. It admits a right adjoint in the homotopy, unstable homotopy category, which is the loop space functor. And so this is simply X with coefficient in omega K A N. And so what we derive from this stability property of singular cohomology is that omega K A N is isomorphic to K A N-1. Okay, so the Eilenberg-MacLane spaces for A fixed are not unrelated. They, on the contrary, they are related by this property. And so this leads topologists to introduce spectra. Maybe you know. So if we want to represent the whole singular cohomology, we want to consider the sequence of all KAN, and let's say HA will be the sequence of all Eilenberg-MacLane spaces like that, KN-1, KAN, and so on. And plus there will be these maps here, but this map corresponds by adjunction, maybe 1, to a map sigma n from KAN-1 to the suspension of it's in the other way. From the suspension of KN-1 to KAN. Okay. So in order to prove, to get some representability theorem, I have to introduce to you some category. So the corresponding category of spectra will be a stable homotopy category and I'll describe only the objects. Objects are just sequences. E is a sequence En of topological spaces, pointed topological, plus some suspension map, if you call like that, from S1 smash En to En plus 1. Okay. So the first example, I've defined it here. This is the Islander-Maclaurin spectrum associated to A, but there are other ones. If X is just a pointed space, one can define the spectrum of infinite suspension of X, which is just the sequence of Sn smash X and in N with obvious suspension map. Okay, so the morphisms in this category are a bit difficult to describe. I don't want to do it now. Let's say that they are based to, first of all, they are just morphisms of each En, which are compatible with the suspension maps, but we have also to localize the category in order to relate weak equivalencies and also to get the following properties. Let's say it's enough to state the properties of SH. So first of all, the category SH top is triangulated. So there are distinguished triangles and rules for them, satisfying the axioms of Verdier. Second of all, the infinite suspension here induces a functor, a well-defined functor, from the unstable category to the stable one. The category SH top is not only triangulated, but it's also monoidal. The product is denoted smash by topologists. This is called a smash product. Okay, and this functor is monoidal. Okay, and moreover, the infinite suspension of the topological circle is equal to the suspension of the triangulated structure on SH top. Okay. These properties basically describe uniquely SH top as the let's say, the initial homotopy category which satisfies this property and with this equipped with this functor. Okay. Now the Brown representability theorem can be recast using stable homotopy. Even a proposition the stable homotopy category from the infinite suspension of a pointed space X with coefficient in this spectrum HA above shifted n times. So this is the same thing as sigma infinity S1 smash product n times smash HA is canonically isomorphic with the nth singular cohomology of X with A. Okay? So what we have in particular is a map H from the category of abelian groups to this stable homotopy category. Okay, and in fact, one can extend this map to the category of complexes of abelian groups, like that, and one can see that. So this is called the Dolcan correspondence. What is used here is the Dolcan correspondence. And I can see that this extension factorizes through quasi-isomorphism of complexes and gives a map like that. So this one I will denote it again H like that. Okay, so now I'm ready to just give you maybe the first theorem of a rational stable homotopy category. The point is that this theorem, which follows from the computation of set of homotopy groups of spheres, says that the map, so in any category, in any triangulated category, you can localize with respect to Q. So the map, which will go from the derived category of Q vector spaces to the rationalization of a stable homotopy category, is just an equivalence of category. Even of monoidal categories, monoidal triangulated categories. Okay, that follows from the finiteness of stable homotopy groups of spheres. Okay, so this is that kind of theorem which I will have in mind to describe the relation between the stable homotopy category of schemes and the derived category of motives, which is a kind of analog of this very simple category. Okay, so now we're going to the theory of Morel and Voevodsky. So I just recall briefly the theory. S is a Noetherian scheme, finite dimensional. And you consider, so delta up S is the category of simplicio Nisnevich sheaves over the smooth Nisnevich sites of smooth S schemes of finite type. Okay, these are the analog of topological spaces or simplicial sets from the topological setting, and out of that we can define H. I'll take pointed again. Simplicial. Put a dot if you want here, and I'll consider the A1 homotopy category of the S as.
Sorry, you wrote delta op?
What? Yeah.
Delta op?
Yeah.
So simplicial is delta op, really?
Yes.
Yeah, that's a contravariant functor from the category delta to the category of sheaves.
Oh, okay.
So that's kind of okay. Usual notation. So it's the, let's say, I'll denote A1 localization just to recall you of the homotopy category associated with delta up over S. So that means that we have inverted two kinds of map in this category. First of all, the map between simplicial sheaves, which induces weak equivalencies of simplicial sets when evaluated at each stalks of the sheaves over its site. And we also invert, example, we invert the map from A1 over X to X, consider as the map of simplicial sheaves for X over S, a smooth scheme. So meaning that we use the affine line A1 as the interval in the topological context. Okay. So maybe just recall to you some example, some nice example of why this category is good due to Morel, essentially Morel-Voevodsky. So let's define P infinity of S to be the colimit in the category delta up shift pointed of S of the following tower. So you take P1 pointed by the point at infinity, you embed it into P2, and so on, Pn infinity. Okay. So you take, this is a kind of infinite projective space. Then a nice theorem of Morel and Voevodsky says that at least when S is regular, I think semi-normal would be sufficient. Then the map from X plus, so X is a smooth scheme, and this means that I have added a base point and consider this as a simplicial sheaf, constant simplicial sheaf. So a map from X plus to P infinity of S computed in the stable A1 homotopy category. These maps are isomorphic to a Picard group of X. Okay. So I assume S to be regular so that the Picard group is homotopy invariant. So in fact, we just need that S is semi-normal. Okay. Just a remark is that in fact, if you recall the book of Morel-Voevodsky, P infinity of S is the classifying space of GM of the algebraic group GM. So in some sense, it is a K GM1 related to this theory. Okay. So other examples of space which represent interesting functors in the unstable A1 homotopy category is the space Z cross BGL, which represent K theory again for S regular, but I'll skip that point. And the thing is that this theory in algebraic geometry is designed to satisfy the same kind of theorem than the one in the topological context, meaning that we want a category in which we can represent cohomology theory in algebraic geometry. And so this is why we need to to get an analog of a stable homotopy category. So we will do exactly the same construction as in the topological context, but topology, geometry, let's say. Instead that we replace S1 by P1 pointed by infinity, like that. So I just denote that P1, seen as a pointed scheme. And so we consider P1 spectra. These are sequences, n of pointed simplicial sheaves over S with suspension map from P1 smash En to En plus 1. Okay. Again, we have in the end, I skip details. After localization of the resulting category, we obtain the stable homotopy category of schemes, SH of S, which is triangulated and monoidal. With an infinite suspension functor from the A1 category to SH, which is again monoidal. Oops. And such that sigma infinity of P1 is invertible for the smash product. So again, in this context, the product in the stable homotopy category is denoted by like that, and it's called the smash product. Okay. Okay, but so the difference is that this time sigma infinity of P1 is not the suspension of a triangulated structure. In fact, one can describe the situation like that. So if we have a simplicial set like that, we can see it as a simplicial sheaves by pointed over S by considering the constant sheaf associated to that. And this induces a morphism from the unstable homotopy category of topological spaces to H of S, which will induce in turn a morphism of spectra such that the following diagram commutes. Okay? So this means that the topological circle S1 is sent to something which I'll denote like that, sigma infinity of S1, and it's just this functor is a triangulated functor, and so this functor is just the simplicial suspension of SH of S, but now it's distinct from sigma infinity of P1, and as you know, there are two spheres in SH of S, which are, and this is why the theory, the cohomology theory in algebraic geometry will be bigraded. So an object of SHS will represent a cohomology theory, and I recall the usual definition of a big graduation on E and M. So this is the stable homotopy class of maps from sigma infinity of X to Sn smash P1, Sn minus 2m smash P1 smash n, and this is smash E, like that. Okay. So the map are computed in SH, and I have thrown away the sigma infinity that I should have put there just to me. So, example of big graduation. If we take the RAM cohomology, X smooth over Q, let's say, or C smooth, then it is it is representable by an object of the RAM is representable an object of SH of Q, let's say, and what I denoted E the RAM like that, and what we have is that E the RAM NM of X is isomorphic to Hn to the RAM cohomology of X. So this is twisted M times. Maybe I'll denote that. So QM and QM is, I think it is the dual H2 the RAM of P1. If I'm not wrong. Okay, maybe there's a sign plus or minus. Okay, so this means that for the RAM cohomology, or for more generally for Weil cohomology, the twists are not seen usually because they does not change the underlying Q vector spaces. Okay, this is what one should call the geometric cohomology. So another example where twists are important is.
Where is QM in the right hand side?
That's defined here. QM is the.
Yes, I can't say M on the right hand side.
Oh, sorry. This is tensor M times. Sorry. True. Sorry. Okay. So these kinds of geometry of cohomology. The same is true for étale cohomology over an algebraically closed field. You won't see any twists up to isomorphism, but there are cohomology theory called absolute, which will have twists, non-trivial twists, and the first one, maybe the most important in motivic homotopy theory, is motivic cohomology. Second example. So this was defined by, let's say, smooth scheme, and again K is a perfect field. So as defined by Suslin and Voevodsky. Motivic cohomology, so I'll denote like that. H and M of X are recalled just the Nisnevich hypercohomology of some complex denoted by Zm, which is a Suslin singular complex. I won't define it here. Or maybe if you have questions for the end of the talk, okay? And from the abstract homotopy theory, and or let's say Voevodsky has proved that this is representable by an object of SH of K, which is denoted by MZ. M. I should say that actually one can extend this. So actually, in fact, Voevodsky defined some spectrum in SH of S and define motivic cohomology in the greatest generative without supposing that we have a base field here as the cohomology with coefficient in this spectrum here. Okay. Maybe another example is Quillen algebraic K-theory. At least when S is regular. So you have a classifying space, BGL infinity, which is a co-limit over n of a classifying space of a general linear group n. And we define, so the notations varies, but I will define KGL to be the spectrum which in degree n is just Z cross BGL, seen as a simplicial sheaf, and so in each degree this is Z cross BGL, and the suspension map are induced by both periodicity by the classes beta. So this goes from P1 smash Z cross BGL to Z cross BGL. Periodicity. So I'll explain in a minute why this spectrum has this form. And the point which follows from theorem of Morel and Wojewódzki is that the stable homotopy classes of map from sigma infinity of X with coefficients in, or let's say, sorry, the cohomology represented by KGL satisfies this property. KGL n m of X is isomorphic to the K theory, so 2m minus n of X. Okay. So the point is that the theory represented by KGL is 2-1 periodic, so it's periodic with respect to P1 because Ky of P1, let's say reduced cohomology smash X is just isomorphic to Ki of X. Okay. This is but periodicity in algebraic K theory, and this isomorphic in fact induces the class beta here. Okay. Okay, so this is the end of a little tour on stable homotopy category. Now the links with motives. So let's recall briefly the theory of Grothendieck motives. I'll take S, just to state this, the theorem, I'll take S to be the spectrum of an algebraically closed film. Okay, then the theory of Grothendieck show motives. Oops. I'll denote that show of K, or this is also sometimes called M rat of K. Okay, is a pseudo-Abelian category, which I won't recall the definition, but I give you some essential properties. Some objects are defined to be h of x, where x over k is smooth and projective or proper. I'll take proper. Okay. Then the morphism between this kind of object from hx, hy are given by the Cho group y, so tensor Q, Cho group of dy dimensional cycles. Yeah. Okay, so it's pseudo-abelian, so it admits so projectors admits kernel in that category, and recall also that any object, it's monoidal, pseudo-abelian. Monoidal category. Any object of Cho K is rigid, meaning it admits a dual in terms of a tensor product, and so in particular this is true for the motive of P1, the Cho motive of P1, which can be written Z plus L. This is called the Lefschetz motive. And the motive of P1 is slightly more than rigid. We have that L is tensor invertible. Okay. So of course, this property reminds us of the construction of a stable homotopy category of schemes. And the link between the stable homotopy category and this category of motifs is quite striking now. It's a theorem which is due to Morel at the origin. He did not publish the paper, but still it's okay. So in this assumption, let's say the first version is that there exists a functor from the category of Cho motives, Cho K, to the rationalization of a stable homotopy category over K, which send the Cho motive of X to the infinite suspension of X with a point added, like that. And this functor is fully faithful. Okay, and in fact this point follows from the stronger statement, which is the following: there exists a canonical triangulated monoidal functor between the stable homotopy category of schemes after rationalization and Voevodsky category with Q coefficients of mixed motif. So this is the stable category of motivic complexes. Defined following Voevodsky. Okay, so in fact, the first point is a consequence of the second one, because the fact that rotating Cho motifs is a full subcategory of dm of k is a consequence of a basic theorem on motivic complexes. Okay, and now if just a remark is that if we consider the conjectural category of mixed motifs, then this category is just the derived category of mixed motifs, and this theorem presents the category of mixed motifs as the analog of the category of Q vector spaces, comparing with the other theorem on that I have stated in the first part on rational topological homotopy category.
I'm sorry, for general K, so the dm is a direct summand of SH.
So K is algebraically closed, right?
Oh, okay.
I've stated that. Okay, so the point is that now.
So that's an equivalence.
What?
So then it's an equivalence.
Yeah. The point is that one can generalize this picture here to any scheme, to any field and to any scheme. First of all, if we consider a field K in which -1 is not a sum of square, then maybe you give you a remark, and this will give you a hint on how to prove this theorem. So in general,
when we look on this map, so what is the analogous of Q vector spaces?
This category which does not exist. Mm-hmm. Okay, so in fact this is this functor which is the analog of the Highlander-MacLane functor. Mm-hmm. Its definition is no, in fact, what you get, so if you consider the unit object Z here in that category, it is sent by this equivalence to the object the spectrum that I have denoted MZ. So I should put Q because this is with Q coefficients. Mm-hmm. Okay, so this is really the analog. But there are more objects than just Q vector spaces, right? See. Any motifs defines an object, so there is something this theorem says that to any mixed motif corresponds some spectrum, but it's in general. So I can describe it to you, but it's slightly more complicated than the Highlander-MacLane theory. Okay, so in general, now if you just to give you a hint on this theory, in general, if K is not algebraically closed, then This is also due to Morel. The category SH of rationally of K splits in two categories. I'll say SH Q plus and SH minus, like that. This category is made of spectra, of P1 spectra E, which are oriented. So oriented means that there exists an action from the Picard group to a cohomology represented by E, so E n m of x to E n plus 2, m plus 1, no, sorry, n, yes. So, in other words, this means that on the cohomology represented by X, there's an action of Chern classes. Okay. If now the spectrum E has a multiplicative structure, which means that there is a multiplicative structure on the cohomology represented by E, then we have Chern classes in that cohomology in the traditional sense. Okay, and this part is made by spectra which are not oriented. So it means that in the rational category, if K is not algebraically closed, then there is another part here of spectra which do not admit Chern classes. And so you see that this is really an obstruction to be an object of DM, because I recall that motivic cohomology H21 of M of a smooth scheme is isomorphic to a Picard group of X, if X is regular at least. Okay, so any object in this category will represent a cohomology with an action of motivic cohomology, and in particular with an action of a Picard group. So this minus part here is an obstruction in general. So, but anyway, what we get more generally is that SHKQ plus is isomorphic to the category dm of K. If we throw away this part here. In algebraic topology, you can see that if you tensor the topological stable homotopy category of Q, then any spectra represents a cohomology which admits Chern classes in the topological sense. And so this obstruction is really something new in algebraic geometry. Now, what time is it? Yeah, just a word about the proof. So the proof of this thing, and even on this one, is just to say that first of all we show that this category dm of K is isomorphic to the category of spectra which admit an action of MZ. Okay. So this is the first step. This theorem is at first due to Rondig's and Ostvar. Okay, and now we use a kind of abstract theory which says that MQ, in fact, with rational coefficients, the motivic cohomology with Q coefficients is the universal cohomology theory which admits an action of Chern classes. So the second step of the proof is to show that motivic cohomology is the universal cohomology which is oriented with Q coefficients. And this universal, into bracket, is in fact what's proven there once you relate to motifs. So I'm sorry I had no time to evoke the notion of Beilinson motifs, but it's hidden in this proof.